It's week 6. We just have we're halfway through the quarter. Your friends at semester schools are like taking finals, and they're going to be done this week. But the joys of the quarter system. It's May. It's already May, right? So here we are. Okay. Well, let's take a look at what we got today. Today we will look at, we'll just start to introduce some classification methods. And the first classifier that we will look at is the Bayes classifier. The Bayes classifier, okay? And this is going to be based off of chapter 5 in our textbook. And so I'm using the same kind of letters and notation that show up in the textbook. If you look at someone else's textbook or someone else's website, they might use different letters, but it's the same idea, okay? So basically, with a classification model, you have training data, and the training data belong to different classes, okay? So, for example, so in our case, we've got n objects, and the training data, we've got information recorded in d dimensions, okay? And those objects have some kind of label, right? They belong to category 1 or category 2 or category 3 or something like that. And we have C of these different class labels that we can have. And the goal is, well, if we get a new observation, can we predict which category it belongs to, okay? So kind of, one of the classic examples is the iris data set. You train it on some of the observations, and you have things like the petal length and petal width and sepal length and sepal width, and then you get a new observation. It says, here's an iris whose petal length is this and petal width is that and sepal length is this and sepal length is that. Can you tell me, is it, setosa or versicolor or virginica, right? So that's kind of your classic example. But it could be a bunch of other stuff too. So a lot of, in marketing, you'll have like, here's a customer or potential customer, and some of the customers eventually bought the product, right? They turned into sales, which is, you got leads and then you got sales. And so perhaps based on past data, you say, okay, here are all of these people that visited our website, or they, did this and they did this. Can we predict who's going to end up making a purchase? And then you invest your kind of marketing money into those people that are more likely to be in the class of sale or something like that, okay? One thing to note is that even though the class labels are 1, 2, 3, whatever, they look like integers, you have to treat them as categories, similar to when you are dealing with like the digit recognition, okay? The output is technically a number, right? This digit is 7, this digit is 2, this digit is 9, but it's important that we treat them as categories, and that we don't treat, the 9 as actually being bigger than the 7 or being bigger than the 2, because there's no size comparison when it comes to just the label of the number, or in this case, the label of the classes, right? And so, it's not meaningful to predict a class label of 2.5 or 2 point something. You either predict it as a 2 or you don't, or predict as a 3 or not. There's nothing in between, okay? Versus something like, if it's a numeric or continuous variable, then sure, it makes sense to predict a value in between, okay? Are you going to make $2 million or $3 million or maybe 2.5 to call it even? That makes sense, but class labels doesn't work, okay? This one, today we're going to look at the Bayes classifier. The Bayes classifier is a probabilistic classifier, in that it's going to return probabilities. And so in our example, I think we have 3 classes, A, B, and C, and what it's going to return is a vector of 3 probabilities, and those 3 probabilities will have to add up to 100%. So it might say class A 19% probability, class B 80% probability, and class C 1% probability. Okay. Another example of a probabilistic classifier is logistic regression, which basically returns a number between 0 and 1, and it reflects a probability. Okay. There's other non-probabilistic classifiers that use kind of hard rules. So, for example, like the k-nearest neighbors classifier or support vector machines, and we'll take a look at these later. We'll just say this object belongs to class C, or class B, or whatever. Okay. Now, one thing to note is that even though we call this the Bayes classifier, and it's because it uses Bayes' rule, it is not Bayesian statistics. So Bayesian statistics, which I'm assuming you've heard about by now, is an entirely different thing, and I cover it in 102C, although I won't be teaching 102C this coming year, so it's a little bit sad for me. But we treat the unknown parameters as random variables, and that's Bayesian statistics. So this is Bayes' rule and a Bayes classifier, but it's not Bayesian statistics. Okay, so review. Bayes' rule. What is Bayes' rule or Bayes' theorem? It's this. And what does this mean? It means you can get the probability of this conditional probability, A given B, with a bunch of other stuff, right? If you need to know the probability of A and B, or the intersection of A and B, and you can get the probability of A and B, or the intersection of A and B, or B and A, in the numerator by doing probability of B given A times the probability of A, and then you divide by the probability of B, okay? And we also know that the probability B in the denominator, we can decompose that into a whole bunch of other stuff, right? So I think this is from 100A, and you like decompose these probabilities into like the probability of B given A for this value, and then probability of B given A for a different value of A, and so on and so forth. And you sum it across all of the different possible values of A. If you consider every possible value of A, that's going to give you the total probability of B. Okay, so we're basically going to use this for our thing. So this is what we want. The goal is we want to figure out what's the probability that this new object belongs to class C. So we wanted to say, hey, what's the probability that this new object belongs to category, belongs to Setosa, all right? And that should be some probability between 0 and 1. Or what's the probability that it's Virginica? Is it some other probability? What's the probability that it's versicolor? Okay, that's for the iris data set, okay? And we're going to base it on all of the information we have. Okay, we have the values for this particular observation. Okay, so x nu would be something like the petal length is this and the petal width is that for this observation. It's the values in this observation, and then we also have all of the training data and basically all of the training data from before, all of the previous observations x and all of their labels t. That's what we're going to base it off. Okay, so we're going to treat our training data as fixed, and everything else. Okay, because it's a probability, all the rules of probabilities apply. So the resulting probability has to be between 0 and 1. Okay, and then if you add up all of the probabilities across all of the possible class labels it can be, those have to add up to 1, right? So if you do the probability that it's Setosa, probability that it's Virginica, probability that it's versicolor, those 3 probabilities have to add up to 1, okay? Or whatever else it's going to be, right? So I keep using the iris data set, and I hope that's okay. You just had a homework dealing with the iris data set, so I'm hopefully using these are fine, right? Okay, so if we got 3 classes, those 3 probabilities have to add up to 1. Okay. So when we take Bayes' rule, which says A given B is equal to the probability of B given A times the probability of A divided by the probability of B, okay, we're going to say the T nu equals C is the A part, the X nu is, this is the A, and then the x new is the v, okay? And then this given x and t, this is just kind of, we're treating it as given or fixed in all of our cases because it's our training data. So that's always going to remain in the given section. So we're going to say the probability that a new observation belongs to a certain category given the values in its observation is going to be equal to, all right, so that this part, we label these in Bayes, in the Bayes rule, we call this part the posterior distribution, okay? This part we call the likelihood, right? It's going to equal the probability of what are the probability of getting those values if it did come from class A, right? So it's kind of like saying, hey, here's an iris, a new iris. It's got this, I'm making up numbers. Let's say its petal length is 1 inch and its petal width is 1/2 inch and its sepal length is 2 inches and its sepal width is 1 inch or something, right? It's not even how it's recorded. It's like recorded in millimeters or something. But let's say this, right? So petal length 1 inch and petal width 1/2 inch, okay? So we say, well, what's the probability that this thing is setosa, okay? And to answer that, because that's what we want to know, we're going to say, well, it's going to be related to, if it were setosa, what's the probability you would get a petal of length of 1 inch and a petal width of 1/2 inch? That's what we want to know, right? If it were setosa, can setosa make petals of this size? Or if it were versicolor, could versicolor make petals of this size? And then when you look at the data, you go, oh yeah, you know what? Versicolor makes totally different sized petals, so that doesn't really make sense for it to be a versicolor type of flower, okay? There's also over here, so that's the likelihood, the probability of observing the observed values that we got if we assumed the new observation belonged to a specific class. This part over here is a prior probability. It's the probability that some new observation belongs to class C before we knew anything else about it. So that's just kind of like saying, you know, if in your data set it was like 90% setosa, then before you even like looked at the measurements in the data, you might say, well, if I had to guess, 90% setosa, okay? So you're just kind of looking at just kind of the class labels before you did anything, okay? And then in the denominator, we have the marginal probability, and it's the probability of getting these values regardless of which class label. And really, this just is there, so everything sums up to 1. But let's take a look. Oh, yeah. Okay, so this denominator here, okay, we're going to just sum, if we think about what this is, right? So if we go back to this and we say, well, we can decompose probability of B into basically what I have here is the numerator, but summed across all possible values of A. I'm going to basically do the same thing down here, okay? So this thing, this marginal probability, it's a little bit, it can be overwhelming. Like, what's the probability I get a petal length of 1 inch and a petal width of 1/2 inch, regardless of what species it is, okay? It's going to end up being the sum of what's the probability of getting a 1 inch petal from setosa, what's the probability of getting 1 inch petal from virginica, plus the probability of 1 inch petal from versicolor, okay? You calculate that probability across all of the possible species or classes, whatever. So you take the numerator and you sum it across all possible classes, okay? And that's what this thing down on the bottom says, okay? And it says, so considering every single possible class, from class 1 to class big C over here, we just take the numerator. So this looks like a mess, right? Like if I just showed you this is the formula and I say, hey, this is how you get it, it could feel a little bit like, that looks a little bit crazy, but it's just the numerator across all possible classes. Okay, so let's do a silly example to illustrate how this Bayes classifier works. Before I do that, let me give you your first view quiz answer for today, which is, what is it? First answer is A. A as in apple. A as in apple. Is the quiz not up? What did I do? What? Yo, you know what I didn't do? I didn't publish the module. click the button. Now refresh the page. Does it show up now? Okay. What was it? A? A. A is an apple. Great. Okay. First answer, A. All right. So I just keep using red and blue marbles because that's simple enough for this scenario here. Okay. So you're going to buy, you go on the internet, you decide you're going to buy a whole bunch of pouches filled with red and blue marbles. And for whatever reason, you decide you're going to buy 25 of these bags of marbles. Okay? And sometimes you shop on Amazon and you're just like, I just need to buy like some simple product, right? Like I just need a new charger for my phone. And then it's like 50 companies offer the same thing, and it's like brands you've never heard of from sellers you've never heard of, and you're like, is this thing gonna catch on fire? I don't know, you know? Like, so anyway, now you're shopping for marbles and you've got 25 different places and stuff. Okay. And then when they arrive, maybe you do some investigation because you're really concerned about this. And so you find out the pouches come from 3 different factories, all right? And then and you go, well, if they're coming from different factories, maybe the different factories have different filling proportions of red and blue marbles and stuff like that. Okay, so anyway, out of these 25 bags, 24 of them are labeled, and we find that half of them, 12, came from factory A, and then a quarter came from factory B and factory C. So 6 came from factory B, 6 came from factory C, and then bag 25, it's not labeled, and we want to try to guess what factory did this come from, okay? Is that all right? This is just a silly thing. So we're going to assume that the bags are filled randomly via some Bernoulli or binomial process, and that like every time they put a marble into the bag, it's got an equal chance of being red or blue, okay? So it might be 50% chance of red or 50% chance of being blue, or 30% chance of red, 70% chance of whatever it is, okay? So here's our training data. We got 25 bags, 24 of them we have labeled, and then this last one, we want to figure this out. Okay, and so you go through, you tally up all of your data. So this takes a while, but you take, out of the 12 bags that came from factory A, you count up all of the marbles. 60% of them are red, 40% are blue. When you look at the bags from factory B, half are red and half are blue, 50-50. And factory C, 40% are red and 60% are blue, okay? Now, we don't actually know the exact filling proportions at these factories, okay? So as far as the factories go, they could be operating something different. And when you open up the bags, there is some variation, but we're not too worried about our assumption that it's a binomial process. Like the data seem to align with that, okay? So we could say, you know, for example, one pouch from factory A has 20 marbles total and 14 are red, which would be 70% red, but another pouch has 20 marbles and 11 are red, 55% red, okay? But overall, factory A, 60% are red is what we're getting, okay? And so that's what we have. So we did maximum likelihood estimation for each of these things. We get 60% red for factory A, 50% red for factory B, 40% red for factory C. Okay, is that all right? So that's the summary of our training data, our 24 bags. And then we take our new pouch, we open it up, and what do we find? Inside, there are 20 marbles, 10 of them are red. So we've got 50% are red in this particular bag. Okay. So based on this, what's the likelihood that it came from any of these factories? Okay. So the likelihood is the probability of observing this specific data. 10 red marbles out of 20 marbles total. Okay. If we assumed the bag came from factory A, or if the bag came from factory B, or if the bag came from factory C. Okay. So here I'm just going to use the binomial probability rule, right? N choose x, p to the x, 1 minus p to the n minus x. So if the bag came from factory A, what's the likelihood I would get this data? 10 red out of 20 marbles? Well, it would be 20 choose 10, 0.6 to the 10 times 0.4 to the 10. I get something around 0.117, around 12%. That's the probability, likelihood of this data, given if we assumed it came from factory A. If we assumed it came from factory B, which is 50% red and 50% blue, then the likelihood is around 18%. Probability here is around 18%, 0.176. And then for factory C, which is everything reversed, 0.4 is 40% red and 60% blue. The probability of getting 10 red out of 20 marbles ends up being 12% as well. Okay, so this is just the likelihood if it came from factory A, B, or C. Okay? So that's the likelihood. But we want to weight this, okay? We want to also factor in the fact that based on just the counts of the data right here, factory A was more likely than any of the other factories, right? Factory A, 12 out of the 24 things came from factory A. So prior to opening the 25th bag, what's the probability it came from a particular factory? So the prior probability would be the probability that some new observation belongs to a certain class before we knew anything else about this, okay? So if we assume that the bags that we received reflect kind of like the manufacturing capacities of the factories, it might be reasonable to assume that factory A is the biggest one, producing half of the marble production or whatever for this company or something. So before we even opened up the pouch, we might have guessed that it came from factory A with a probability of 0.5, or it came from factory B with a probability of 0.25, or came from factory C with a probability of 0.25. Okay. All right. So far, okay for the prior probabilities? Okay. And so what we're going to do is let's calculate the numerator, the probability of the likelihood multiplied by the prior probability. Okay. And so this is, for class A, what's the likelihood of getting 10 red if the bag came from factory A multiplied by the probability that it came from factory A? So we're going to take around 12% times 0.5. We get something around 6%. Okay. What about factory B? Okay, class B. So based on what we see in the bag, factory B has the highest likelihood. Okay, class B has the highest likelihood, around 18%. But then it gets weighted down a little bit because class B only produces 25% of the bags. So if we do that, we get something around 4.5%, 4.4%. Okay, and then class C has the same likelihood as class A, but its own factory produces a lot less. So we're going to multiply this by 0.25, and we get something a little under 3%, 0.029. All right, is this okay as far as getting these numbers here? Okay, and so these are basically the numerators for our three classes. And we're going to turn all three of these numbers, numerators, into probabilities. Now, if I add these three numbers up, they will not add up to 1. So basically, I'm going to just take these three numbers, and I'm going to just multiply them by a factor, or divide by a factor, so that all of them add up to 1, okay? And so to do that, I'm going to divide by the sum of the numerators. So we're going to take, so the marginal probability that goes in the bottom is just these numerator values added up, okay? When I add all three of these numerator values, okay, 0.058, around 6%, 4.5, 0.044, and around 3%, 0.029. If I add all three of these numbers up, I get something around 13%, 0.013. Or I'm sorry, 0.1319. Okay? So I'm just going to take the numerator and I add them up for all three possible classes, A, B, and C. And if you had a whole bunch of classes, you got to add them all up. And that's just the law of total probability. And so here, this number goes in the bottom. The other, the number that I had earlier, 0.0585, just under 6%, goes in the top. And so when I do this fraction, I get 0.444. Right? And so now that I'm going to divide all of the numbers by 0.1319, everything will add up to 1. So if I do the numerator, this one, divided by this 0.444. This one becomes 0.334, and this one becomes 0.222. Okay. So here I rewrote everything. Kind of, we're just using, again, this is just Bayes' rule. A given B is equal to B given A times the probability of A divided by the probability of B. And it's going to be the class probability that belongs to class A, given our data that we observed and all the other training data, is going to be, what's the probability of getting what you observed, 10 red, assuming that it came from class A, which has P equal to 0.6, times the probability it came from factor A, which is 0.5, and then what's the probability of getting 10 red, regardless of factor, which is the sum of the numerators. Okay, so we get 0.44, 0.33, and 0.22. So those three numbers will add up to 1, which is good. And there's our answer, okay? So what's the probability that this bag came from class A? It's now 44%. What's the probability it came from class B? 33%. What's the probability it came from class C? 22%, okay? So we don't have an answer. When you do classification, it's just a probabilistic number, and none of these are majority, but if that's what we observed in our bag, these would be the resulting probabilities, okay? So, one thing to kind of put this into perspective and, just see how this classifier works is, when we look at the bag ended up being 50% red, okay? 50% red. And so if we were to base our classification only on kind of what proportion in our bag is red, which is 50% red, we would probably pick factory B, because factory B, according to our training data, produces 50% red, whereas factory A is 60% red and factory C is 40% red. So that's what we have. But we also take into account the prior probabilities of our data. The prior probabilities of our data said, factory A produces a lot more bags in general, and factory B only produces half as much as factory A. So when you take that into account, okay, then factory A, which started off prior to looking at the data, started off with a 50% chance of producing a bag, drops down to 44%. And then factory B, which started off at around 25%, goes up to 0.33, and factory C, which started at 25%, now goes down to 0.22. Okay, so we're taking into account what we see in our data and calculating the probabilities based on that. Okay, so we're combining the likelihoods and the prior probabilities. Factory A ends up the most probable one, but only most probable by a little bit, 44%. Okay, we made some pretty strong assumptions though in all of this. Okay, so number one, we assumed that when we looked at all of our training data and we got 60%, factory A was 60% red, and we're assuming that's the case for factory A. That's a strong assumption. Okay, we're assuming that the estimates that we got from our data are reflective of how things are working at the factories. Okay, and then the other assumption was that the proportion of bags from factory A in our sample reflects the proportion of kind of bags that they manufacture. So in our sample, we said 12 out of the 24 bags came from factory A. Therefore, when we observe a random bag in the future, there's a 12 out of 24, 50% chance that it came from factory A. Okay, so that assumes our sample's representative of the proportions in the population. Okay, so if you have outside knowledge, you should incorporate that. For example, maybe you're familiar with marble manufacturers and you're like, oh, you know what? Your sample happened to be 50% coming from factory A and 25% came from factory B and 25% came from factory C. But in reality, we actually know that all three factories, A, B, and C, all have the same manufacturing capacity. And so, anytime you buy a bag in the future, you have a 1/3 chance that it came from any of the three factories, right? So that's possible. And so if that were the case, then ignore the counts that you got in your training data and just use 1/3 as far as your prior probabilities. Okay, so the situation, your domain knowledge will affect how you model your prior probabilities. think, in the coming homework assignment. So homework 4, which you have to look forward to. You'll do some classifications. You'll do the iris data set, okay? And as far as the iris data set goes, there's 3 classes: Setosa, Virginica, Versicolor. And we're just going to assume their prior probabilities are 1/3 each, okay? And I don't know what it's like in nature. I don't know anything about irises or flowers, right? Who knows? What's the most common species of iris out in nature? I don't even know. I couldn't even name species of iris other than these 3 just from this data set, right? so I have no idea. But you know, maybe some, what would you call them? A flower gardener? There's the florist who sells the flowers, but then the person who farms the flowers and grows them, they're not florists, right? That's like something else. Flower farmer, maybe. Doesn't sound quite right. But it's a different job than the florist who makes arrangements and procures them and stuff. Okay, but anyway, somebody in the, do we know? A botanist? No, that's someone who studies flowers.
It's like a farmer, but just for flowers.
Yeah, there's farmers for flowers. No, the gardener maintains your garden. Maybe, okay, we would just call it a flower farmer, I think. I know, right? Yeah, it's like, you go to, you know, what is it? The Netherlands, and you see all those fields of tulips. The person who farms all of those tulip farms. Floriculturist.
Yeah.
Okay. All right. That sounds about right. Okay. Maybe that person knows. Oh, versicolor. We don't even bother making versicolors. They die in the sunlight, so Setosa, that's the one we go for. Yeah, I don't know. Who knows, right? We have to buy the organic irises. I wonder what the I haven't seen organic flowers being sold at the market. Okay. Anyway, all right. Same example, but let's try this out. Okay. This time, we're going to we open up our bag, and what do we get? Only 6 of them are red. Okay, 6 out of 20. So only 30% in our bag are red. And so now we go, okay, well, could this have come from factory A? Could it have come from factory B? Could it have come from factory C? Okay, our bag is only 30% red. Okay, so, you know, factory A fills up at 60% red. It's possible that factory A produced this bag. It just, whatever reason, only a couple red marbles ended up in the bag. Okay, it's also, it could come from factory B or factory C. I mean, it's lower. What we have in our bag, only 30% red, is lower than any of these manufacturing things. But when you do the likelihood calculations, okay, factory A ends up being the least likely, 0.002, around 2.5 out of 1,000 chance of producing this bag, okay? Whereas, what's the probability it came from factory B, okay? Less than a 1% chance, 0.009, okay? And what's the probability that it came from factory C? At factory C, the fill proportion is 40%. So this is the most likely factory to produce a bag where only 30% are red. And I'm sorry. Actually, all of these things I'm multiplying by its prior probabilities already. So when you do this, it ends up being 0.03, okay, around 3%. So if I take this and I multiply by 0.5, I get 0.002. Take this likelihood times the prior probability, I get 0.009. Take this likelihood and multiply by its prior probability, I get 0.03. And so when you add up all 3 of these things to get our denominator, the marginal probability is only 0.042, okay? Which just says, you know, this bag, this denominator number is kind of just like, what's the probability you just get a bag where only 30% of them are red, okay? And it's pretty unlikely based on the factories that we have. It's unlikely. There's a 4% chance that it would happen, which is, I mean, it's not impossible, but it's not that likely, okay? And so when we take each of these numerators and divide by the marginal, then then our proportions, our probabilities become this. Okay, there's a 5%, around a 5 or 6% chance that it came from factory A, 21, 22% chance that it came from factory B, and around a 72, 73% chance that it came from factory C, indicating that when you see a bag and only 30% of the marbles are red, okay, 6 out of 20 are red, then factory C becomes the most likely manufacturer for this particular bag, okay? And so even though, according to our training data, half of the bags come from factory A, because factory A fills at 60% red, it's very unlikely that it came from this factory. And so this ends up being the calculations here. All right. Does that kind of make sense as far as this Bayes classifier goes? So that's the Bayes classifier for this kind of simple, like binomial example. Okay. So here's the explanation there. Okay. So now we're going to kind of take the same concepts of the Bayes classifier, and we're going to still use the Bayes classifier, but we're going to apply it to I think, a little bit more of a useful scenario here. Let me go ahead and give you your second view quiz answer, which is the letter, what did I do? E. E as in elephant. E as in elephant. Second view quiz answer. E. E as in elephant. Okay. Mixtures of multivariate Gaussians. All right, so we have the multivariate normal distribution, and we said this is the PDF. And what I'm going to have is I'm going to create a mixture of these things, okay? And so one thing to remember is that if the off-diagonal elements are 0, it's basically just a product of univariate ones. So here I have 3 classes. I've got class A, class B, and class C. And I'm going to generate data from each of these things. And so I'm going to use, there's a package, MVT norm, multivariate normal, and it comes with basically the MV norm functions. So you're used to D norm and P norm and R norm. So D norm to get your densities and R norm to generate random values. Basically, we have the same thing except it's R and MV norm for random multivariate normal values and stuff. And here I'm going to generate 30 values from the random multivariate normal, and it's going to generate 2-dimensional values because the vector, the mu A, the mean is a vector of length 2, and the sigma matrix is a 2x2 matrix. Okay, so it's 3, 0, 0, 1. So 3, 1 down the diagonal, 0 on the off diagonal elements. Okay. Class B has a mean at 0, 0, and its sigma matrix is the identity matrix. Okay, so the contours of class B will be concentric circles at the origin, right? Because the variance in the x1 direction and the variance in the x2 direction are the same size, 1 and 1. And then class C is going to be centered at 2, -2, okay, 2, -2, and it has covariance. So its variance in the x1 direction is 3, its variance in the x2 direction is 3, but there's covariance between x1 and x2 of 2.5, indicating that there's covariance between the two. And I'm going to bind all 3 of these things together into one big matrix X. And here, R does not normally plot contour lines, so I'm going to just I plotted them using ellipses and stuff like that, and this code is just there if you don't want to parse through it, no biggie, okay? But this is what the data look like here, okay? So this one is centered at 2, 3, this one's centered at 0, 0, this one's centered at 2, -2. The variance in this direction is 3, and the variance in this direction is 1 for this one, and they are independent so that the variance and covariance, variance x1 and x2 lines, major and minor axes of the ellipse are perpendicular. major and minor axes of this, now I guess circle, would be perpendicular as well, centered at 0, 0. And over here, there is covariance between x1 and x2, and that's why we have this. But the variance in the x1 direction is 3, variance in the x2 direction is 3, and this is what we have. Okay, and these are values generated according to this. Okay, so in our training data, we have all of these labeled as red, blue, and green. And what we're going to do is we're going to say, hey, you know what? Let's put in a test case and let's try to guess which class it should belong to, right? So if we have an observation here, it's easy. It should be red. If we have an observation out here, it should be green. Observation over here will be blue. But then what if it's something like right here? Okay, then it's like maybe a little bit red and blue. And if it's over here, maybe red or green or something like that. Okay, now we generated our data, so we know exactly the mean and we know the variance matrices used to generate this data. But in general, when you are trying to do some kind of classifier, you probably don't know the actual mean of the population or the variance of the population. You got to estimate these based on what you have. So with our data, we're going to estimate the mean, and we'll estimate the variance and covariance matrix using the data. So the maximum likelihood estimate of the mean is just the sample mean. Okay, so it doesn't get much easier than that. You just take the observations that you have. So I'm going to just say, hey, what's the mean of the XA values? What's the mean of the XB values? What's the mean of the XC values? Okay, so the true value I think was 2, 3. And when we took the mean of our sample, we're getting 2.2 and 2.8. And the true mean of the generating data was 0, 0. And when we took our sample means, we're not getting quite that. We're getting 0.3 and negative 0.1. And then we take, I think the true mean for C was 2, negative 2. And we're getting something a little bit different, right? But that's just sampling variation. And we have the sample means here. Okay? All right, how about, what if we wanted the maximum likelihood estimate of the variance? Okay, basically it's your sample variance, except you're dividing by n. Okay, now you could say, well, you know what? Let's do sample variance and I want to divide by n minus 1. Okay, that's fine also. All right, you just have to make a choice whether you're going to divide by n or n minus 1. So maximum likelihood estimation divides by n. If you want to try to get the unbiased estimate of the variance, you would use n minus 1. So a little bit of a difference, little trade-offs and compromises. But basically, this is how you would just calculate your sample variance. And in our case, you know, in matrix notation, it would just be you take your x values, subtract off the mean, and then you take that resulting matrix, transpose times this resulting matrix, and basically you get kind of the sum product of all of the deviations from the mean, which would be your variance and covariances. Okay, so this was maximum likelihood. Okay, and then again, the unbiased one is the same thing, but divided by n minus 1 rather than n. Okay, and so here we can get the variance estimate just by running the variance. Right, you can call var on a matrix, and it will give you this thing. Okay, so if you just do this, and this is what we get. Okay, so you call variance on a matrix with 2 columns, it gives you a 2 by 2 variance matrix. This is what we have. Oh, something happened with the printing there, but that's fine. Okay. And again, we're expecting something close to 0 for the off diagonals for these two, and then we get something that's not 0 for this one, which is what we want. Okay, and so if I plot the estimated contour lines, this is what we have. So if I say, all right, let's assume we have a multivariate normal centered at the mean from our sample and using the sample variances, this is what the contour lines would be. And so to just kind of contrast, so these are based on our samples, and then the true ones are a little bit off, right? So if I go back a few slides. Okay, so the true ones, these are perpendicular, centered at 0, 0, centered at 2, 3, and centered at 2, negative 2. Now, over here we get something just a little bit off, right? So this is, in black, we had the kind of the values we use to generate the data, and then over here is what we get based on our samples, our estimates. Okay, and so we're going to use that to calculate the classification for a test case. So here's a test case. We're going to put it right at 0, 0. And we're going to say, what class does this belong to? Okay, now visually we look at this and go, all right, it's blue. Okay? And hopefully our Bayes classifier, when we run it through it, will also say it should be blue. Okay? Now, it works well here because it's two-dimensional. But, you know, in higher dimensional settings, it's actually not that easy because even with like the iris data set, which is 4-dimensional, you have to be kind of creative with how you're going to plot it. You might have like a whole bunch of pairs plots and things like that, or you try to plot this in some 3-dimensional thing, but the data itself is 4-dimensional, so how you plot something is a little bit trickier, and it's not quite as easy to visualize. Now, in the iris data set, a lot of the variables are highly correlated, so you can drop a variable and not lose that much information just because the variable you dropped, if it's highly correlated with other ones, kind of that information is captured anyway. Okay, so this is what we'll do. We'll do this next time, and we'll run the Bayes classifier. Okay, let me give you your last view quiz answer for today, which is the letter D. D as in dog. D as in dog. Okay, so we'll end here for today. Have a good rest of your day. We'll see you all on Wednesday.